All right, we're going to continue in chapter 5, which is gases. All right, Avogadro's law. Right on here. All right, so if we have a reaction that is all gases, say C4H10 gas plus oxygen gas produces CO2 gas and H2O gas. All right, now this has to be given as a temperature higher than 100 degrees Celsius, or water is labeled as gas and you don't need a temperature. All right, so all these would be gases at 25 except for water. But in this case, I'm at higher than 100 degrees Celsius, and so I have water as a gas. The key is every reactant and every product must be a gas. All right, and to balance that, we need 2 of those, we need 8 of those, and we need 10 of these, and we need 8 and 5, 13 of these. All right, so now we have a balanced chemical reaction. And for any balanced chemical reaction, you can look at it in terms of moles. And you would say 2 moles of butane will react with 13 moles of oxygen to produce 8 moles of CO2 and 10 moles of H2O. All right, moles always can be used. You can only use volumes if everything is a gas. So all reactants and products are gases. And so then and only then, when all the reactants and products are gases, then you can use volumes. All right, and so you would say 2 liters of butane gas would react with 13 liters of oxygen gas to produce 8 liters of CO2 gas and 10 liters of H2O gas. Again, they all have to be gases. All right, so a problem for this reaction, which could be done in moles, but it would be a lot easier if it were done using the liters, would be, where is that? All right, so we will go with this. Let's say I have, let's see, 20 liters of C4H10, and I have 30 liters of O2. Calculate limiting reagent, theoretical yield for CO2 gas. All right, and I want the theoretical yield in liters of CO2. And so you would then, if they gave you, they could say at, well, they can give you some, they could say, let's say 770 millimeters of mercury and, I don't know, 500 degrees Celsius, some temperature above 100 because water is in the gaseous state. All right, so you have enough information to use PV is equal to nRT and convert everything into moles. But if you have, if you see that everything there is a gas and we can use volumes, that makes the question a lot easier. You would have to do PV is equal to nRT, convert that into moles, PV is equal to nRT, convert that into moles. Then you would do the mole ratios, get moles of CO2. Then you would have to use PV is equal to nRT to convert that into liters of CO2. All right, so a much easier way is you see that they are all gases. And so you would just say 20 liters of C4H10 All right, you have your volume ratio. 2 liters of C4H10 will produce 8 liters of CO2. And you see that that would give you 80 liters of CO2. Do the same thing with your 30 liters of oxygen. 30 liters of oxygen. 30 liters of oxygen. All right, and then we have our mole ratio, our liter volume ratio, since everything is a gas. Our oxygen, 13 liters of oxygen will produce 8 liters of CO2. This one you need your calculator for. You have 30 times 8. And divide that by 13. And you have 18. All right, the 2 sig figs, it would be 18 liters of CO2. All right, and then just like we did for the last test, the smaller amount, that is your theoretical yield, and this oxygen is your limiting reagent. The smaller amount comes from your limiting reagent. All right, so then they could also say in lab, I don't know, 15 liters of CO2 was produced. And then you would have the percent yield. And so you would have 15 of the possible 18 theoretical. Again, they have to be the same units, and they are, times 100. And so you take your 15 divided by your 18, and you get a 83% yield. All right, so you can do the theoretical yield, limiting reagent, and percent yield using just volumes if, that is the key here, if all reactants and products are gases. You can always use moles. You can only use volumes when all the reactants and products are gases. Again, you would get the exact same answer if you use PV is equal to nRT, convert all these into moles. Mole ratio, then once you get your moles of CO2, then you convert that to liters by PV is equal to nRT. It would be a lot more time consuming, but would give you the correct answer. All right, we already went through standard temperature and pressure. Remember, 0 degrees Celsius, but you'll never use Celsius. 273.15 Kelvin and 1 atmosphere. All right, so the volume of a gas at STP to 3 sig figs is 22.4, to 4 sig figs is 22.41, and that is in liters per mole. So any gas at STP is 22.41 liters per mole. If you have 1 mole of argon, you got 1 mole of helium. If you have 1 mole of a gas at STP, it is always 22.4 liters in volume. All right, so again, PV is equal to nRT. That is going to be very important. There are going to be a lot of questions using PV is equal to nRT. Again, R is going to be given. It's going to be given to 4 sig figs, 0.08206. And the units will be listed. Liter atmosphere per mole Kelvin, and that's important because then you know that pressure has to be in atmospheres because that's what we have in the R value. The volume has to be in liters because that's what we have in the R value. All right, N is always moles and T is always Kelvin. Every one of these R values is mole Kelvin, mole Kelvin, mole Kelvin. All right, so all of them are mole Kelvin. Now your pressure and your volume, here is kilopascals and decimeters cubed. If that's the R value you want to use, then you got to convert all of your pressures into kilopascals and all of your volumes into decimeters cubed. And you can do that if you want to. I am never going to do that. Every time I use PV is equal to nRT, it is liters, atmospheres, moles, Kelvin. This is the only R value that I will use when I use PV is equal to nRT. And that number is going to be given. All right. All right, so I don't think we finished this one. All right, so what is the mass of nitrogen in the cylinder is the question. So PV is equal to nRT. When the question is, what is the mass? All right, you can solve for moles. And once you solve for moles, you know that your molar mass is mass per mole. And so once you have moles, you take your molar mass times the moles that you get, and you will have the mass of for your answer. All right, so pressure, 17.1 atmospheres. Volume, 50 liters. N is what we're solving for. 0.08206 liter atmosphere per mole Kelvin. And then you have your 23, you add 273.15, you have 296 Kelvin. Kelvin cancels the Kelvin. Liters will cancel the liters. Atmospheres will cancel the atmospheres when you divide both sides by R and by T. All right, and so then you'll get your moles of nitrogen. And so when you get your moles of nitrogen, that is going to be 35.20. That's the wrong sig figs. That is 35.2. All right, and when you take your 35.2 moles of nitrogen, which you have to remember is N2, now you have the moles of N2 per gram of N2. So that is not just 14.01, it is two of them, 28.02. And when you push the buttons there, you get 986 grams. So that is the mass of nitrogen in a 50-liter cylinder at 17.1 atm and 23 degrees Celsius. All right. So there's going to be PV is equal to nRT. You're going to have to solve for P. You're going to have to solve for V. You're going to have to solve for N. Possibly you have to solve for T. That's kind of rare. When we do our lab on Thursday, we're actually solving for R. So when we do the lab on Thursday, we are calculating R. In order to get R, we have to have our pressure and our volume and our moles and our temperature. So in lab on Thursday, we are going to get pressure, volume, moles, and temperature of oxygen gas and see how close we get to 0.08206. All right, all the conversions. So not only are we solving for pressure, volume, moles, R, and temperature, you'll also solve for mass over volume, which is your density. You'll also solve for molar mass. And so your density is the pressure times the molar mass over RT. Your molar mass is your density RT over P, or MRT over PV, all right, because mass over volume is density. All right, so you will not be given any of these equations. Make sure you know how to get to them or memorize them. No equations except for a real gas equation is given, but ideal gas and any manipulation of the ideal gas is not given. All right, so we did this one as well, density. All right, so if you go back, you have your density, and it is right there. So that is your pressure, your molar mass over your RT. All right, so we have our 3.50 ATM. We have our CH4, 12.01, and 4.04, 16.05. And then we have our 0.08206 liter atmosphere per mole Kelvin. And then our temperature, 273.15. So that is going to be 398. All right, so the Kelvin cancels the Kelvin, the moles cancel the moles, the atmosphere cancel the atmosphere. All right, and you'll know if you do the units, you'll know if you have the wrong equation or not, because density has to be grams per liter. This is the right equation. So you multiply 3.50 times 16.05, divide by 0.08206, and then divide by 398, and that will give you the density of 1.72. This is methane, yes. 1.72 grams per liter. All right, so there will be definitely a question like that on the test. You solve for density. There will be one that solves for molar mass. All right, let's see what this one is. All right, so we have a 500 milliliter flask containing a sample of octane, a component of gasoline, placed in boiling water bath in Denver, where the atmospheric pressure is low at 634 millimeters of mercury. So there's a pressure, here's a volume, and the water boils at 95.0 degrees Celsius. Here's a temperature that you add 273.15 to. The mass of the vapor required to fill the flask is 1.57 grams. What is the molar mass of octane? All right, and then what is the molecular formula? All right, so when we want to find molar mass, what do we need? We need the mass over the moles. All right, so they gave us the mass. It is 1.57 grams. All right, so we have the mass, 1.57 grams. Now all we need is the moles. All right, and so it is then using PV is equal to nRT. All we need is PV divided by RT. So in order to get moles of a gas, we need pressure, volume, and temperature. R is a constant. They gave us a pressure, they gave us a volume, and they gave us a temperature. And so we can find moles. And once we find moles, we plug it in right here, and then that will give us our molar mass. All right, but we have to get it into the correct units. None of these are in the correct units. In order to get the correct units, we have to remember R. R is 0.08206. Again, that's going to be given, liter atmosphere per mole Kelvin. So you have to give your volume in liters. So 500 milliliters is 0.5 liters. Now that is the right units. Atmosphere, 634 millimeters of mercury. You have to divide by 760 millimeters of mercury is 1 ATM. And so when you take your 634 and divide by 760, you get 0.834 ATM. Now you've got the right units for pressure. And temperature is always in Kelvin. And so when you add these up, you get 368.15. So that is 368.2. Kelvin. So now your temperature is also in the right units. So you take your pressure, 0.834, times your volume, 0.5, divided by the 0.08206, your R value, and then you take that divided by your 368.2, and you get your moles. So when you plug all those in the correct units, you get a 0.0138. 0.0138. So when you take your 1.57 and divide by your 0.0138, you get 114. All right, so that is your molar mass. Now, the empirical formula is C4H9, so we have to find the empirical mass. All right, so 12 times 4, that is 48, plus 9, that is 57. So we take our 114 divided by 57. So we're getting an N value. That's the molar mass divided by the empirical mass, like we did on the last test. And that gives us 2. And so our molecular formula is C8H18. All right, so they're going to give us enough information to find a molar mass. Once you find that molar mass, you have the empirical formula given, and now you can figure out what your molecular formula is. Your molecular mass divided by the empirical mass is going to give you an integer. You'll also know if you did this wrong. If you do not get an integer, then you have calculated the molar mass incorrectly. All right, so they did it a little different. They went to density. And again, you're going to get the exact same answer. It doesn't matter how you did it. All right, so they took the mass over the volume and got a density. And then they did the dRT over P, and they went right to the molar mass. All right, and so they plugged in all the numbers. So again, they're going to end up doing the same thing. We took the mass and divided by the moles. Use all the same numbers. How you do that, it doesn't matter if you do it this way or if you do it the way that I did it. Either way is fine. Again, if you get 114, then you did it correctly. All right, stoichiometry and gas volumes. All right, so here we're going to do in lab, we're going to take KClO3 and we're going to balance it for you. 2 KClO3, and that's a solid. And then we're going to have a catalyst, MnO2. When you have a catalyst, you will write it on top of the arrow. Then we're going to heat it. Delta indicates heat. When you heat your KClO3, it decomposes into KCl solid, 2 of them for balanced reaction, and 3 oxygen gas. All right. So when we do this in lab, you're gonna weigh your test tube that has KClO3 and MnO2. Then you're going to heat it, and then you're going to weigh it again. It's going to weigh less because the oxygen was released. And so you're going to use conservation of mass, all right, in order to get your mass of oxygen. So you're going to use conservation of mass to get mass of oxygen. All right, so let's see if I can find a problem using that equation. Make another one up. All right, here's my question. How many grams of KClO3? Would be required to provide 4 liters of oxygen? At 25 degrees Celsius and 748 millimeters of mercury. All right, so in this case, note that I put solids and I put a gas. These cannot be done in volumes. These can only be done in moles. So when you read it, it is 2 moles KClO3 reacts to produce 2 moles of KCl and 3 moles of oxygen. If they were all gases, you could use volumes. These are not all gases. You have a solid there. And so you can only use moles. All right, so the only thing we can use is moles. So we're going to take our volume of oxygen, our temperature of oxygen, and our pressure of oxygen. And so we have PV is equal to nRT. Note that you can only use PV is equal to nRT for oxygen. You cannot use PV is equal to nRT for KClO3 because it's a solid. You cannot use PV is equal to nRT for KCl because it is a solid. You can only use PV is equal to nRT for gases because it is the ideal gas law. It can only be used for gases. All right, so we have a pressure, we have a volume, we have a temperature. R is a constant. We can solve for moles of oxygen. And once we get moles of oxygen, we do the mole ratio to get moles of KClO3. Then we use the molar mass of KClO3 to get our answer. All right, so we solve for moles. So moles is your PV. When we divide both sides by RT, that's going to give us our moles. So pressure has to be in atmospheres. All right, because the R value is in atmospheres. So we take our 748 millimeters of mercury, we divide by 760 millimeters of mercury in 1 atmosphere. So we take our 748 divided by 760, and that gives us 0.984 atmospheres. The volume has to be in liters, and it is 4 liters. The R value is given 0.08206 liter atmosphere per mole Kelvin. And the temperature has to be in Kelvin always. All right, so 273.15 plus 25, 298 Kelvin. All right, and so now we have everything canceling except for the 1 over mole is the units, and so we invert multiply. N is always in moles. So we multiply the 0.984 times 4.00 divided by 0.08206 and divide that by 298, and we get our 0.161. That is moles of oxygen. All right, so then we do the mole ratio from the balanced chemical reaction. 3 moles oxygen are produced from 2 moles of KClO3. And then we find the molar mass of KClO3, which is 122.55 grams per mole of KClO3. So we multiply it by 2, divide it by 3, and then we multiply it by the molar mass of 122.55. And we get 13.2. It's almost 13.1, but I got 13.2 grams again here. If you actually plug in that number, 0.161. I didn't clear my calculator. Times 2 divided by 3 times 122.55. That would give you it should be a 0.2. 13.2 grams. That is correct. Of KClO3. But again, if you had, there's uncertainty in that too. It's a 0.15, which rounds to 0.2. All right. Again, you can't do a volume ratio because they're not all gases. All right, so we use the ideal gas law to find moles, and we use the mole ratio. So we are going to use stoichiometry using gases. Another example, when a 2-liter bottle of concentrated HCl was spilled, 1.2 kilograms of calcium carbonate was required to neutralize the spill. What volume of CO2 was released by the neutralization at this pressure and this temperature? All right, so you have your CaCO3, we have HCl. We know that a carbonate with an acid is going to give CO2 and water. And so we get CaCl2 plus CO2 plus H2O. All right. And so in this, we have solid, we have aqueous, and we have gas, and we have liquid. All right, so the only gas that we have for PV is equal to nRT is CO2. All right, so CO2 is the only gas that we have. All right, so when we have this balanced chemical reaction, everything is 1 to 1. All right, so we have what volume of CO2? So we're looking for the volume of CO2. It is a gas, so we need the moles of CO2. R is a constant. We need the temperature of CO2, and we need the pressure of CO2. Here's the pressure that needs to be converted into atmospheres. Here is the temperature that needs to be converted into Kelvin. So now we got to figure out how do we get moles of CO2. All right, and in order to get moles of CO2, we have a mass of calcium carbonate. And you can convert this mass of kilograms into grams of calcium carbonate, use the molar mass, convert it into moles of calcium carbonate, and then use the 1-to-1 mole ratio to get moles of CO2 that we can then put into our PV is equal to nRT to solve for the volume. All right, so we have 1.2 times 10 to the third grams of CaCO3. Then we need the molar mass of calcium carbonate, which I don't have. Calcium is about 40 and 12 and 48, so we're talking about 100. So it's very close to 100 grams per mole of CaCO3. And then the key is the mole ratio. 1 mole of CaCO3. Do not put the moles of CaCO3 into PV is equal to nRT, because again, that is not a gas. That is not a gas. That is not a gas. That is the only gas is CO2. And so you can only put moles of CO2. Unfortunately, or whatever, the moles are the same because the mole ratio is 1 to 1. But you need to show that you are converting that to the moles of the gas in order to put it into the ideal gas equation. All right. So there is the setup there, 100.09. All right, so then your moles to 2 sig figs would be 12. So you're going to get 12 moles of CO2 produced. All right, so now we have everything we need to solve for the volume. We have moles, we just calculated it. We have our 735 millimeters of mercury that we take and divide by 760 millimeters of mercury per atmosphere. And that will give us our 0.967 atmospheres. We take our 20 degrees Celsius and add 273.15, and that gives us our 293 Kelvin. And then we plug it in, 12 moles, the R value that's given, 293.967. And since they gave us 1.2 kilograms, which is 2 sig figs, we will give our answer to 2 sig figs. This would be 12 moles. All right, you're going to give 2 significant figures for the volume of your CO2. All right, and that they give to the wrong number of sig figs. That should be 3.0 times 10 to the second liters. All right, I'm not sure why they're saying 3 sig figs. Go back to the original question. Yes, 1.2 kilograms. That is 2 sig figs. All right, so again, that is 2 sig figs. And when they give the answer, it should be to 2 sig figs. But they gave it to 3. And not only did they give it to 3, they actually said it's 3. That is wrong. 2 sig figs. All right, 3.0 times 10 to the second liters. It is 300 liters of CO2. All right, so now we're going to have a flask, and we're going to put some gases in this flask. So here is our flask, and it is sealed up so that the gases will not escape. I'll call it gas A, and I'll call it gas B. So I have two gases in this flask. All right. So when I'm looking for the pressure total is going to be the pressure of gas A plus the pressure of gas B. And if I had more gases in there, you have to add up the gases, all the pressures of all the gases to get the total pressure. All right. All right, so that is Dalton's law of partial pressures. You add up all of the pressures of all the different gases, and then that is your total pressure. All right, so that's this one right here. So it doesn't matter how many gases you have, you add them all up, and that will give you your total pressure. So that's called a partial pressure. So you have one flask, you have a partial pressure for A, a partial pressure for B, and then you add those up, and then you have the pressure total. Dalton's law of partial pressures. Add up all the pressures of all the different gases, you have the total pressure. All right, so here is a problem where we're going to add up a bunch of gas pressures. In a 100 ml sample of air exhaled from the lungs is analyzed and found to contain this many grams of nitrogen, this many grams of oxygen, that many grams of CO2, that many grams of water vapor at 35 degrees Celsius. What is the partial pressure of each component and the total pressure of the sample? All right, so all of these are air. All of these are gases: nitrogen gas, oxygen gas, carbon dioxide gas, and water vapor. So that's water gas. And we are given a temperature, and that is 35 degrees Celsius. All right, so we need to find the pressure. So again, PV is equal to nRT. All right, so the pressure is nRT divided by V. So for the first one, to get moles, you need moles of nitrogen. You're going to take the mass, 0.0830 grams of nitrogen, and divide by the molar mass, which is 28.02 grams per mole of nitrogen. That's how you get your moles of nitrogen. Your R value, 0.08206 liter atmosphere per mole Kelvin. Then your temperature, 35, you add 273.15, and that gives you an 308 Kelvin. And then you divide that by the volume, and they told you that the volume of the sample was 100 milliliters, and so that is a 0.1 liter. All right, and so this number is a constant. It's always the same. And so we have the same gases, we have the same volume, that they're all in the same container. They have the 100 mil sample of this air. All right, so it's in a 100 mil flask. All right, so they all will have the same volume. They all are at the same temperature. All right, so the only thing that's going to change is this part. All right, so when you do oxygen, you're putting in the 0.0194 divided by 32.00 grams per mole. All right, those numbers are the same. You're going to get an answer. Your CO2, 0.00640 divided by 44.01 grams per mole. All right, so you just have to convert all those to moles and then multiply the moles by RT divided by V. And that's going to give you the partial pressure of all of those components. All right, so again, so this one, and this one, all the same. This one, all the same. This one, they are all the same. The only thing that's changing is the moles. And you simply get the moles by taking the mass divided by the molar mass. Mass divided by the molar mass. Mass divided by the molar mass. And so here's your partial pressure of nitrogen. Here it is of oxygen. Here it is of CO2. And here it is of H2O. And then you add them all up. to get pressure total. You add the 0.749 plus the 0.153 plus the 0.0368 plus the 0.0619, and that gives you your total pressure. All right, which in this case is 1 atmosphere, which is the wrong sig figs. All right, so you got 3 decimals plus 3 decimals plus 4 decimals plus 4 decimals. You need to have 3 decimals, and I'm trying to add those up. That's a 7, carry the 1, 10, 20, and then 2, 0, 1. Let's see, that's 2, 0, 1. All right, so that's going to actually be a 1 when you add those up. So to the correct sig figs, 1.001 ATM, because that is a 7, which would round that up to a 1. All right, so sig figs are not right, but the idea is you just add up all those numbers, and that gives you your total pressure. All right, so if you have the partial pressures of all of these things given, what is the mole fraction? All right, so this one is interesting. So when you want a mole fraction, which has this letter chi, it is simply the moles of component A, whatever gas A, over moles total. Add up all the moles. All right, now for a gas, all right, multiple gases in the same flask. So let's say we have A, B, C, and D in here. That's A, B, C, and D in here. 4 different gases in there. So we have 4 different gases in this flask. PV is equal to nRT, just like we did last time when we calculated those pressures. The volume, well, all the gases are in the same 1 liter container or 100 milliliter container or whatever size the container is. The key is they all have the same volume. Whatever volume the container is, that's the volume of A, that's the volume of B, that's the volume of C, and that's the volume of D. Gases fill the container. All right, R is a constant, and they're in a container, the same container, in the same room. It's the same temperature. And so when you take your P and divide by N, all right, then you have, on the other side, you got your RT divided by V. And since they have the same temperature, because they're in the same flask in the same room, and they have the same volume because they're in the same flask. All right, so they have the same volume and they have the same temperature. And so your pressure over your moles is equal to nRT over V. That is a constant. All right, so you can look at pressure total and moles total. You can look at pressure of A over moles of A. And that is equal to RT over V. And so you can set those things equal to each other. And so you have your pressure total over moles total is equal to your pressure of A over your moles of A. All right, now we can solve for moles of A over moles total. So let's multiply both sides by moles of A, and so that gives you moles of A over moles total. We have to get rid of the pressure total, and so we have pressure of A over pressure total. All right, so all I did was I took this equation and I solved it for moles of A over moles total. And now you see that the pressure fraction is the same as the mole fraction. Since you have the same volume, the same temperature, and R is a constant, moles of A over moles total, that number is exactly the same as taking the pressure of A over the pressure total. And so when they're asking for the mole fraction and they only give pressures, you have to remember that the pressure fraction is exactly the same as the mole fraction when you're talking about gases. So if you want the mole fraction, you have to add all these up. And when you add all these up, 8 and 8, you have 760 millimeters of mercury total. All right, so if you wanted the mole fraction of nitrogen, you take your 570.0 divided by your 760.0. That is your mole fraction for nitrogen. If you want the mole fraction of oxygen, you take your 103.0 divided by the 760. That's your mole fraction of oxygen. All right, so a mole fraction is moles of A over moles total. But for gases, that is also equal to the pressure of A over the pressure total. So that makes it very simple. You simply take the pressure that they gave you, add them all up, and then you have your different fractions. Of course, when you're done, the mole fractions of all the gases in the flask will equal 1. So you add up all your mole fractions, it'll be 1. If it was mole percent, multiply it by 100, you would get 100%. All right, but the key is you have to know that a mole fraction is moles of A over moles total, but for gases, that is exactly the same as the pressure of A over the pressure total. All right, so in lab, we are going to collect gases over water. All right, and when you see this phrase, collecting gas over water, you always have to use the pressure total is equal to the pressure of whatever gas you are collecting, the gas that you're collecting, plus the pressure of water vapor. And this you get off of table, it used to be 5.6. Anyway, there's a table in chapter 5 that gives you the pressure of water at different temperatures. Oh, it's right here, 5.6, that is correct. Table 5.6, so you don't memorize that table, you just say the temperature is 23 degrees Celsius. I know this one at 23 degrees Celsius. The pressure of water is 21.1 millimeters of mercury. All right. And you're going to be given in lab the pressure of the day. That's the pressure total. Will be given. And then you look up the pressure of water. And you have to then take your pressure total and subtract the pressure of water to get the pressure of your gas. And we will pick up there tomorrow.